This video is all about mass to mass or grams to gram stoichiometry in chemical equations. Remember that stoichiometry is just a fancy term for the math of chemical reactions. For example, if I know how many grams of a reactant I'm putting into the reaction, I want to be able to calculate through stoichiometry how many grams of a desired product I'm going to be able to make. Okay, so we really need the molar mass of compounds in the balanced chemical equation in order to do mass to mass stoichiometry. So we need the molar mass from the periodic table all added up for the relevant compounds that we're interested in the balanced equation. So let's say that we know how many grams of a substance A that we are putting into a reaction, for example. We need to know the molar mass of substance A to find how many moles of substance A we have. Then we're going to go to our coefficients, our mole ratio from the balanced equation. We're going to look at those coefficients and use them to convert from moles of A to moles of a new desired compound, moles of B. And then we'll need the molar mass of B in order to convert to grams of B. So we need the molar mass of A for our first conversion. We need the coefficients of A and B in the balanced equation for our second conversion. And then we need the molar mass of B for our third and final conversion. So it's really, I see it as a three-step process. I suppose you could see it as a four-step process if you thought writing down the known at the very beginning was a fourth step. So 3 or 4-step process depending on how you look at it. So let's get started. Okay, our first example says how many grams of glucose can be synthesized from 28.7 grams of water in photosynthesis. So this is like photosynthesis that occurs in plants. We've got a balanced equation. 6 molecules of carbon dioxide react with 6 molecules of water to form 6 molecules of oxygen gas and 1 molecule, it's implied 1 C6H12O6 or 1 glucose molecule. Okay, so our known here is 28.7 grams of water. So we would really start with that. We would write down our known 28.7 grams of water, and that's our compound A. We'll put that over 1. So our A is water. Then, just like we would normally do in a unit conversion, we would bring down grams of water into the denominator so that we'll be able to get rid of it. From grams of water, we have to first convert to moles of water. So we'll want to go to moles of H2O. Here's where that 2-part unit just becomes so vital. To do that, we need the molar mass of A, of water. So we're not given that. We were given the molar mass of glucose. But we can calculate the molar mass of water. We know it's 2 H's and 1 O, so we break out our periodic table. So do that now if you need to. You can pause. Hydrogen is 2 times 1.008 on our table. And oxygen, there's 1 oxygen, an implied 1. Oxygen atom is 16.0. And so if you need to, you can go find our video on calculating molar mass of compounds to review. But when we add those up, we should get 18.02 grams, or we can call this grams per mole for water. So this really means that there are 18.02 grams are equal to 1 mole for water. So whenever we have water, if we have 1 mole of it, the mass or molar mass is 18.02 grams. So what we can do here is put the 18.02 with grams are in every 1 mole of water. So put a 1 with moles. Cancel out grams of water. And then in our next step, we need to bring down moles of water because we will want to get rid of that. The problem doesn't want us to know about water in the end, it wants to know about glucose in the end. So our compound B is going to be our glucose, or C6H12O6. Okay, so to get from water to glucose, we have to first be in moles, because to switch compounds, you have to do a mole-to-mole conversion. So we have to first be in moles of water and use the mole-to-mole ratio or coefficient from the balanced equation. So we're going to get from moles of water to moles of C6H12O6. And we're going to look at the balanced equation and say, well, 1 mole of glucose is produced when 6 moles of water go into the reaction. Okay, so for every 6 moles of water. Now moles of water cancel. Wish I could say we're done. I'm just kidding. You maybe wish that. But it is kind of a long process. We have one more step. We're at moles of glucose, and we need to still get to grams of glucose. So what we're going to do is we're going to bring down moles of C6H12O6. Sorry, I kind of ran out of room, so I'm just going to squash my unit in here. And we want to convert that to grams of C6H12O6. So we need to know the molar mass of glucose to do that. Luckily, we were given that. That makes our job a little easier. We could have calculated it with our periodic table, but it'll be a little less work. So that means that there are 180.2 grams of glucose in every 1 mole. That's what our molar mass tells us. And so moles of glucose cancel for units. So we are finally left with grams of glucose, which is great because that's what we were trying to find all along. Now we just have to do the math, multiply the fractions. So when we do all that, what are we doing in our calculator? Well, we're taking essentially 28.7. I won't put the times 1 because that won't really change anything. Anything by 1 multiplied by 1 is still itself, right? So we've got 28.7 times 180.2 is all we've got on our numerator. In our denominator, we have 18.02 times 6. Now we have to be careful that both of these get in the denominator in our calculation. So parentheses around the denominator is a necessity if you're going to do that all at once. Maybe it's hard to remember where to put parentheses. Some folks just always do parentheses around their numerator and their denominator before they hit that slash and divide them. I think parentheses around both is great for good measure. Okay, take a second, calculate that, and you should get 47.8 grams of glucose, and glucose was C6H12O6. I'm just like running out of room for my little 6, but I do like to always have units there. So that should be 47.8 grams of C6H12O6 for our first example. Okay, let's try another one together because I think that we probably need a few examples before we're going to feel confident. This next practice problem says how many grams of O2 can be made from the decomposition of 100.0 grams of lead oxide. And this is actually lead 4 oxide, but anyway, PbO2. Okay, so we've been given 100 grams here for our starting material, but the question is how many grams of O2 can be made. So that's what we don't know. We don't know how many grams of oxygen we can make. Okay, so how can we get started? Well, let's just write down our known. Let's write down 100.0 grams PbO2. And let's put it over 1. Okay. Then, without even thinking, we're going to start doing this on autopilot. We're going to bring down our known. Grams of lead 4 oxide. And we want to right away get from grams to moles because it's only when we're in moles that we can convert between substances. And luckily, we were given the molar mass, 239.2 grams are in every 1 mole. That's a big help. Okay, then we bring down moles of PbO2, and we're trying to get to oxygen. Now, we can't go straight to grams of oxygen, even though that's what the problem wants. We have to first do a mole-to-mole conversion, because that's what we can do with our coefficient. That's how we get from one substance to another, is we do this mole-to-mole conversion with our coefficients. So, in front of PbO2 is a 2 for 2 moles, and then it produces 1 mole of oxygen. So every mole of PbO2, of lead oxide, produces 1 mole of oxygen gas. Okay, but the problem wants grams of oxygen, not moles, so we have one last step to do. So we bring down moles of oxygen, and we need to get to grams of oxygen. We'll need the molar mass of 2 oxygen atoms to do that. So, somewhere on the side, maybe you want to calculate the molar mass for 2 oxygen atoms is just 2 times its mass of 16. And you would get 32 grams per every 1 mole of O2. So the 32 goes with grams, 32.00 grams are in every 1 mole of O2. We can cancel out moles of O2, and finally the units match up, and we've gotten to grams of O2 like we were supposed to. Okay, now we just do the math in our calculator. 100.0 times 32 divided by 239.2 times 2. Now we have to have parentheses around that denominator to do it all at once. Around the numerator and denominator is surely just fine. It's always helpful. Take a second, grab out your calculator, pause if you need to, and you should get 6.689 grams of oxygen gas are produced from the decomposition of that 100 grams of our starting material. Okay, I know we still need more practice because this is a lot of steps. But these next type of problems, they're still going to give us that practice because we're still going to be going through these same steps when we find theoretical yield. What's theoretical yield? Theoretical yield is the maximum amount of products that can form. So this problem says, what is the theoretical yield when 0.552 grams of aluminum reacts with excess chlorine? So what this means is we have all the chlorine we could ever possibly need. We have excess chlorine. Aluminum limits our production. We're going to call that later a limiting reactant. But this, let's just say limit. I meant to just put limits for now. Limits how much aluminum chloride we can make. It limits us to a certain amount of aluminum chloride. So we can only make the amount of aluminum chloride that we have enough aluminum to make. So let's figure out, how much is that? How much aluminum chloride can we make from our aluminum? We know we have all the chlorine we need, so we can kind of ignore it, basically. So we start off with 0.552 grams of aluminum, and we put it over 1. That's our known. And then we bring down our units, our gram of aluminum. And from grams, we can always get to moles of our substance because we can use that substance as molar mass. Hey, aluminum is kind of easy. We just check on the periodic table and find out that, hey, on our table, we've got 26.98 grams per mole for aluminum. That's its atomic mass, so that's its molar mass as well. And then we bring down moles of aluminum. Now we can get to the compound we want, which is aluminum chloride, AlCl3. And we can do that with a mole-to-mole conversion using the coefficients of the balanced equation again. So the steps are kind of molar mass, coefficients, and then they're going to be molar mass again. Molar mass, coefficients, molar mass. That's kind of the overall big picture of what we're doing in terms of steps here. So we already did a molar mass. Now we're at coefficients. 2 moles of aluminum chloride are produced for every 2 moles of aluminum that react. And then we'll cancel out our moles on the numerator and denominator. And we'll bring down our moles of aluminum chloride because we don't want to be in moles. The problem wants us to get all the way to grams. Theoretical yield usually does imply grams of the product. So we want to get to grams of aluminum chloride that can form. That last step, we'll need the molar mass of aluminum chloride, but we were given that one, 133.34. So let's put that with grams. Molar mass, because it is a mass, goes with grams, and it tells us the grams per mole per every 1 mole. So we put 1 with mole at that point. Okay, moles of aluminum chloride cancel. We have gotten all the way to grams of aluminum chloride, which was our job here. Now we just do the math. You know, 2 over 2 cancels in fractions. We can get rid of that. I think it's a little bit easier too. Then in our calculator, it's just 0.552 times 133.34 divide by 26.98. Since there's only one number on the denominator, you wouldn't need parentheses. Maybe you feel like, I don't feel confident when I'm going to need parentheses and when I'm not. It never hurts to put parentheses around a numerator and denominator. You won't go wrong that way, so you could try that. Whatever works for you, you should get 2.73 grams of aluminum chloride. So you can try that in your calculator right now and make sure you get the same answer that I did. All right, I have one more theoretical yield problem for you. Okay, this one says, what is the theoretical yield of Si3N4 made from 14.57 grams of silicon and excess nitrogen in the reaction? Okay, let's go for it. It's saying that you have all the nitrogen you could ever possibly need, so you don't need to worry about that. And that what you'll run out of is silicon. Okay, so we want to find out if we have 14.57 grams of silicon, when we run out of it, how much product will we have made? Okay, so we're going to write down our known 14.57 grams of silicon and put it over 1. And then we're going to bring down our unit, grams, SI. And for that, we just have to grab out our periodic table. So take a look at yours, 28.09 grams of silicon should be on our table, or in every 1 mole of Si. Okay, so those grams cancel. We are going to bring down moles because we've done molar mass. Next is coefficient. We'll look at the coefficients, the ratio in the balanced equation of silicon to the product. So let's write the product formula. For every 1 mole of product that's produced, 3 moles of silicon have to go in. So we'll cross out moles of Si. And our last step, we've done molar mass. Next up is coefficients. And lastly, we need to do our last molar mass step. Coefficients, molar mass, molar mass, coefficients, molar mass is kind of our progress here. Okay, so bring down moles of Si3N4, and it's our lucky day we've been given the molar mass. So when we go to get to grams of Si3N4, we've been given that. In every 1 mole, there's 140.28 grams. We do tend to give you some of these bigger molar masses just so your problem doesn't depend on getting those right, since, you know, we're more apt to make mistakes then. Okay, when we multiply our fractions, we get 14.57 times 140.28, and then divide by 28.09 times 3. Now, if students make mistakes, it's not getting all of that in the denominator. If you don't use parentheses and you do it all at once, that 3 will pop up in the numerator on you, and you won't want that. You can do parentheses around both the numerator and denominator. Never hurts. And you should get 24.25 grams of Si3N4. Okay. I think that I lied and said that was our last example, but we have one more on theoretical yield. It's almost hard to tell what's different about it. This one is saying that you have excess silicon, all the silicon you need, and that your nitrogen is limiting you to 14.57 grams of nitrogen actually limits our reaction and runs out. So the reaction is going to stop when we're out of nitrogen this time. So let's see how much product we can make this time. So we'll start off with 14.57 grams of nitrogen and put it over 1. Now, we did a problem so similar, so this would be a great place to pause and see if you can do this problem yourself. Okay, did you pause and try it? I'll show you the answer so you can check it. We're going to bring down grams N2 and get to moles first and foremost, molar mass. We know in every 1 mole of N2, there's 2 nitrogen atoms. Well, let's go ahead and calculate that molar mass. 2 times 14.01 on our table for nitrogen is 28.02 grams per mole, right? Or 28.02 grams are in every 1 mole of nitrogen. Okay, so cross out grams of nitrogen, those units cancel. Bring down moles of nitrogen. We did molar mass, now we're on coefficients. We need the coefficients between nitrogen and our product molecule. Okay. We know that 1 mole of product is made for every 2 moles of nitrogen that go into the reaction. Okay, we did coefficients and molar mass. Excuse me, we did molar mass and coefficients. So it's molar mass, coefficients. Now we're on molar mass again. We need molar mass of our product to wrap this up. So we bring down moles of Si3N4. We want to get to grams of Si3N4. And we're going to use the given molar mass. We're so lucky. We got this molar mass in our problem. 140.28 grams are in every 1 mole. Cross out mole. So we did molar mass, coefficients. Here's our last molar mass step. That's really our pattern. Molar mass here, coefficients, molar mass. All right, let's do this math. Let's multiply these fractions, kind of skipping down here. 14.57 times 140.28 divide by 28.02 times 2. Do parentheses around your numerator. Parentheses, is really required around that denominator. Something to make sure 2 ends up in the denominator. And calculate that. You should get 36.47 grams. I hope maybe you paused and got just that. And I'm hoping that you're feeling ready to do gram to gram calculations, including those that ask you for theoretical yield for upcoming problems.